Hello everyone, and welcome to another lecture in computational algebraic geometry. Today we're going to talk about the topology of hypersurfaces. So that means I'm going to be looking at smooth hypersurfaces in Pn+1, so that x has complex dimension n. Let's say d will denote the degree of f, the homogeneous degree, and let me write it down that x is smooth. At least we know how to check for smoothness, and we take it on from there. And let's visit n equals 1 case again. So what does n equal 1 means? X has dimension 1, so x is a curve in a plane. So of course, whether or not it's in a plane doesn't matter. We said that if x is a curve, x is going to be of this shape. So the topology of x fits within the classification of real surfaces, and it will look like a bunch of donuts glued together, or the surface of such donuts. But for example, if n equals 2, so let's work over the complex numbers. So the complex dimension of the set of complex solutions of x is n, so 2. That means the real dimension is going to be 4. And now it's much harder for me to draw a picture like this. So I want to answer the question, what does x look like? Drawing pictures is going to be much more difficult, and I'm actually interested in every n, and beyond this n, it's basically impossible to understand this by drawing pictures. Okay, so this is the goal for today. Describe the shape of x, and I would like to imitate the situation with n equals 1. So by shape, I want to understand, let's say, the topology, something at the core of x. Well, I can tell you what the answer should look like, and it's simply that we should look at the homology groups. And for now, let's say we want to look at all the homology groups for every k. So I'm now going to explain what they are, but it will turn out that actually one homology group is the only one that matters. Let's go back to our curves. So when n equals 1, the first homology groups is the set of points up to equivalence. So this is generated by any point. Any point is equivalent to any other point. X is path connected. So this is just set h1 of x of z. Remember that we said this was basically generated by a bunch of loops, and this has dimension z 2g. This is rank 2g. The h2 of x, so this is dual to h0. This is just generated by the total space, so the homology class of the total space. Nothing interesting. And of course, this is also rank z. And we will see a similar structure that always the middle homology group is the most interesting one. But let's look at it here. This rank 2g gave us the shape of x because we had a classification of real surfaces. Whenever you knew this h1, you know x is oriented, you know it looks like this. So it's not going to be as easy in higher dimensions, and what we will do is that we will be able to compute these ranks, and in analogy, that is essentially good enough information to understand the shape. But we don't have an analogous second step where from the ranks we will be able to completely describe the shapes or draw them. Okay, so let's settle this case where I said only the middle homology group is interesting. So this is actually a very important theorem. So this theorem is stronger than how I will use it here. I will apply it to hypersurfaces, but it's called Lefschetz hyperplane theorem. And I'm going to combine this with Poincare duality. So if you're interested in proving it, those are the two ingredients. So the statement goes like this. So you say, take hk of x of z. So x, remember, is a hypersurface in Pn+1. So I take the kth homology group. You know there is an inclusion into hk. So just take any cycle. It's in x. X is in Pn+1. So it's a cycle in Pn+1. And the statement is that this is an isomorphism when k is less than n. So this gives us the lower half of the homology groups, because we will be able to compute these homology groups. We know what they are, and I will compute them in just a second. And the second half we get by Poincare duality. It's a little bit trickier. So the statement is that hk of x z, and so let me say that already this will be k greater than n, and this thing will be isomorphic to hk plus 2, that's a 2, Okay, so these are isomorphic, except I want to describe the map between them as a part of the theorem. It actually goes like this. So you go, okay, I'm out of space, so I'm not writing the z's. So this is the cohomology, dualized. And then this is also isomorphic to the cohomology, but this time this has dimension 2m plus 2 minus this is 2n minus k, and this is pn plus 1. And I need to dualize because this was homology, this is cohomology. Okay, now the statement is that these two are isomorphic. And how so? Well, any cohomology group, any cohomology class, I can pull back to x from here to here. You can pull back. I would normally have a map going from right to left, but I've dualized, so I have a map in this direction, and it's an isomorphism. So I'm saying this to explain where Poincare duality appeared. It was the Poincare duality appeared here and here. This gives me this isomorphism. Lefschetz hyperplane theorem is here. So the statement here is actually cleaner, but this is slightly more elaborate to prove. The Lefschetz hyperplane theorem gives you something about cohomology groups where the indices are small. So here you use Poincare duality. So let's do this example with n equals 1. So let's say k equals 0 is one of them. I have a curve, and I'm saying this inclusion that maps a point to a point here is an isomorphism. Well, this is clear, so this is also path connected. These are both groups isomorphic to z. And the other thing is h2. So h2 of x of z, which is generated by the class of x, should go to h4. And this is also generated by the class of the space itself. So these are both z's, and this is an isomorphism. But the way this isomorphism works is that this is equivalent to h0, the cohomology group h0, and this is equivalent to h0, and you pull back h0 from here to here. So h0 is very simple, going to be described by constant functions. Well, okay, so to do this in general, I need to tell you what the topology of Pn looks like. And the idea is to use a recursive structure on Pn plus 1. So that means the following. I have an affine space. So maybe I call this the locus where a linear functional is invertible. So this is affine and open. And moreover, the complement of this thing, so the complement is the 0 locus of x0. This is isomorphic to Pn. So it's a hyperplane at infinity, if you want. With respect to this affine chart, this will be the hyperplane at infinity. Now that I have Pn, so in the complement of an plus 1, I can reiterate this process. Pn will break down into an affine set, an affine open, and its complement, which will be Pn minus 1. I write. Okay, so here equality should be taken with a grain of salt. Of course, I'm not talking about the topology on the right-hand side, so this is just a union, so it's like a set-wise union. But the structure is a little bit better, so that the closure of this thing minus this thing itself will have this decomposition. So this is called a stratification. In fact, this is an affine stratification. And such a stratification, if it exists, is extremely restrictive on the topology of the ambient space. By the way, this is a point. And there's a general theorem that says, I'll give a reference for it in the description box. So if you have an affine stratification, then the homology groups is completely generated by the closures of the strata. An here, its closure is Pn. Well, that Pn can be viewed as a homology cycle and of dimension 2n. So that will be a generator at degree 2n. That's what it's saying. So an affine stratification determines all the homology groups, and the generators are the closures of each strata. And when we apply it to Pn plus 1, we find the following. So the hk of Pn plus 1 is going to be one of the following. First of all, each of these affine strata, well, they give me a complex manifold. Their closures give me complex manifolds. Complex manifolds have even dimension. So if k is odd, there's nothing here. And when k is even, then I'm just taking the closure of the appropriate thing here. So the closure will be p, k over 2. And I take the homology group. So k is even, k over 2 is an integer. It will be one of the things here, or the closures of it. And of course, this is a group generated by this thing, so z times that. To summarize this a little bit, we say hk is the rank of this hk Pn plus 1z, and I list 0, h1 up to the top dimension. and this just is 1, 0, 1, 0, and it ends with 0, 1. Well, in that case, our job is almost done, because I'm saying that via Lefschetz hyperplane theorem, I can compute all hk, since I relate it to hk of Pn plus 1, except for hn. Let's go to that. Now what we want to do is to compute the rank of the middle homology group. So rank of hn. So here, remember, x is a hypersurface and the dimension is n. So the complex dimension is n, which means I can go up to h2n in my homology group. So the real dimension is 2n. So this is the middle group. I should also mention that this comes from universal coefficient theorem, and what we know about Pn is that all hk's are torsion free. Or to put it in another way, hk is isomorphic to z to, let's say, bk. These ranks are called the Betti numbers of x. And of course, we know all bk except bn, and that's what we want to prove now. And since we know all intermediate terms except bn, we can use the following fact, that the Euler characteristic of x, which is just the following sum, has the following interpretation, that so unless I made a silly mistake here, all the terms that I do know appear at even index, so the sign is a plus, and then there should be ceiling of n over too many terms where k is greater than n, and then the same number of terms when k is less than n. Hence, we get this expression from here, and of course the term that I do not know, which means computing the Euler characteristic is equivalent to computing the middle term. The Euler characteristic, well, this is defined exactly because it's super nice and has the special, well, many different ways of computing it. And here's one way to compute it. So this is a general theorem about manifolds. This is going to be the degree of the top Chern class of the tangent bundle. So you don't need to know what this is, because I'm not going to follow through on this calculation. So I'm going to give a different calculation. But the reason I'm writing it is that if you know about Chern classes, this is a very easy calculation at this point. So let me give this as an advanced or bonus exercise. Okay, so you should do this only if you know about Chern classes. But what you use is that first the tangent bundle of x maps to the tangent bundle of Tn plus 1, which I restrict to x. And then there's the normal bundle of x. Remember, I said the normal bundle of x is the restriction of a line bundle from Pn plus 1. So x has degree d, it's the restriction of the degree d line bundle to x. And then we have the Euler sequence, which describes the tangent bundle of Pn plus 1 in terms of these simple line bundles. So this is the trivial line bundle, this is the line bundle O1, and you take the direct sum of n plus 2 copies. Well, now the Chern classes behave well with respect to short exact sequences, and to compute this, I just need to use the Chern classes of these line bundles, and that gives me the Chern class here. Then to compute this, I just need to know the Chern class of that, which is coming from a line bundle again. So all of these calculations become super simple. But the formula is rather messy. I'm not going to write down the formula, I'm going to write down a better formula from which you can recover this. But this is an exercise, use these to compute. And Pnx should be a formula, closed formula in n and d, the degree of x. Okay, now I'll do something a little bit more advanced on the homology and cohomology groups, but it will actually come in handy later on. And we will get a more refined expression that will also give us this Betti number, and it will be super easy to evaluate. So don't worry, I'm not going to explain what Hodge decomposition is in the last few minutes, but I will write down a decomposition because I need to refer to the dimensions of this decomposition. So the thing is, I now want to look at the cohomology. So the cohomology, remember, is the middle homology in this case, dualized, and we tensor with complex numbers, right? So this is isomorphic to C, P, N. And the point is that this space actually admits a decomposition, so a vector space decomposition, where it's convenient to use two indices, P and Q, but they just sum to N, and both of them have to be positive. And then this decomposition has these subspaces called HPQs. I'm not giving you any information, I just said there exists such a thing, so let me give the names. So this is called the Hodge decomposition, where the middle pieces actually have a very clean interpretation. So the HPQ is isomorphic to HQ of x of omega p. What that means is that I'm computing the qth cohomology group of the sheaf of P differential. When X was a curve, we only looked at H0 of omega 1. That was the global sections of the sheaf of 1 forms, holomorphic 1 forms. So in general, you need to use these more complicated groups. So if we are being completely honest, Hodge gives a different description of these middle groups, and this isomorphism, which is canonical, is usually referred to as Dolbeau decomposition, or this identification as Dolbeau's theorem. Well, okay, so I only introduced this to define numbers, so you can ignore almost everything here. I just want to define the following numbers. These numbers are h, p, q, and here instead of x I want to write the degree of x, d, because these numbers will not depend on x, and this will be the dimension of HPQ. So I use a smooth hypersurface of degree d. The answer does not depend on my choice of that hypersurface. And also note that p plus q is n, so I'm going to do one more thing, that I'm not going to fix n, so that whenever you give me p, q, and d, I'm just going to go to an ambient space of dimension p plus q plus 1, take a smooth hypersurface of degree d, and then define this. So that allows me to increase the dimension. And the reason I want to do it like this is that now these numbers fit into a very clean generating series. And now comes this very beautiful result. This theorem is attributed to Hirzebruch, but I will give you a reference. I took it from the book of Arapura on complex algebraic geometry. And there will be references in the info box. So here's what we're going to do. We're going to define the generating series HD, which is a sum like this, where P, Q are just positive integers. And then here I'm going to write H, P, Q, D. So this D is fixed. P, Q I allow to vary. And remember, they don't have to sum up to a fixed number now. I just increase the dimension. And I need to correct this by something very small. Well, there's a reason we need to correct this. We'll see this again in the next lecture. But this is 1 if P equals Q and 0 otherwise. So it's essentially HPQ. And what makes this a generating series is that I'm going to put these dummy variables. So this is an element in the formal power series in X and Y. And the theorem says that HD has a very clean expression as a rational function in X and Y. Okay, so then H of D equals 1 plus Y, D minus 1, minus 1 plus x, d minus 1, divided by 1 plus x, d times y, minus 1 plus y, d times x. Okay, so the statement is that I've written a rational function here. This admits a power series expansion, and you just compute this power series expansion and read off the terms. And these terms will give you the dimensions of the Hodge groups. I don't want to just leave you with that. Let me show you how, let's say, Sage Math handles this expression to give you the Hodge numbers. Okay, so I opened up Sage and I'm going to define the following. So first of all, I'm going to define a power series ring over the rational numbers. QQ stands for the rational field. My generators will be called X and Y. That's the expression for generating power series. Then I define a function called HD. So it takes D and returns this rational expression that I just defined. So this is the rational expression from the theorem, except my x and y are from power series ring. That means Sage will automatically expand this thing out. So let's see what h1 says. h1 is 0, which is right. If you think about it, h1 gives me a projective space, and the projective space has this intermediate dimension, but we've subtracted this Dirac delta, so when d equals 1, this HPQ equals Dirac delta, we've computed the topology of a Pn, right? And therefore what we find is correct. H of 1 should be 0. Let's do H of 2. So this is now a quadric hypersurface. So the first thing to observe is that there is nothing of degree 1, for example. And we know that a quadric curve is a P1, and again there will be nothing in the middle. On the other hand, a quadric surface in P3 will have a middle Hodge number, so H11, equal to 2. So the coefficient is 1 here, and then there was this Dirac delta, and that's the right answer. So, and this surface will not have the other numbers H20 or H02. They don't appear here. So this is how you interpret it. And let's do something more interesting. So 3 is very interesting. For example, a cubic curve has H10 equal to 1, H01 equal to 1. Indeed, a cubic curve is genus 1, and the dimension of its holomorphic forms is 1. And it gets more interesting as the dimension increases. Let me look at H4. So, okay, a degree 4 plane curve is genus 3. Let's look at surfaces. So a degree 4 surface in P3 has H20 equal 1, H02 equal to 1, and H11 equal to 19 plus 1, so 20. In particular, the Betti number of a quartic surface is 22. All right, I would like to leave you with this for today. We have one more lecture to do, and in that lecture, I would like to talk about periods of hypersurfaces. See you then.